Okay, we'll get started now. Hello, everyone. My name is Ali, and I'm a student here at Stanford. I also have the pleasure of teaching the one-unit C++ class that we offer called CS106L. And it's basically a class that over 10 weeks covers industry-level standard C++ programming and all those sort of concepts related to real-world C++. So today, I think Marty and Ashley were kind enough to let me lecture today, and because they see the value in covering the sort of importance behind learning actual C++ on top of the concepts you've learned in this class. So today we're just sort of going to get a wide overview of C++ and how it looks in real life, and sort of the concepts you can take away, so that if you do encounter C++ code in real life, you'll know how to sort of navigate your way around it. So the game plan for today, we're going to start with just a quick introduction on what we're doing today, and then we're going to dive right into some advanced C++ features like templates. We're going to talk about the standard C++ collections, which are sort of the analogs of vector, map, and set and all that in actual C++. And then we're going to talk about this thing called iterators and algorithms, some other neat features if we get time. And then we're going to try and look at actual C++ code in the wild. So we're going to find some repository that's interesting and kind of look at how that code looks and if we can parse it in any sort of way. Okay, so before we begin, I do want to give a disclaimer. Everything you learned today, please do not use in your final exam because we sort of spent 10 weeks going over these concepts and learning the nuances, because you can shoot yourself in the foot really easily. So sort of take this as a guide to the future as opposed to what you should use for your exams. Okay, so don't use any of these things. Okay, so before we begin, I thought it would be a good idea to sort of take a moment and think about where you've come and what you have done over the course of this 10 weeks. If you remember your sort of first lecture in 106B, you were told, you pound include IOStream, you have this int main thing, you see out hello world, and then it prints hello world for some reason. Something's called endl for some reason, right? And then you've come all this way where now you have a thorough understanding of all these incredible programming concepts like recursion, graph algorithms. You know how to use vectors and maps and linked lists. You know how to manage memory using the stack and the heap. All these really incredible things, which if you think about it, it's astounding that you've sort of mastered in 10 weeks, right? So at the end of 106B, it's important to realize that in this class you've learned all these useful, incredible ideas which aren't actually computer science specific in any way, in that you're learning how to solve problems in a systematic way. You're learning how to solve problems using computers in a systematic way. Now, in any sort of problem you might try solving, there's sort of, I think, 2 to 3 things you need. A professor of mine used to say this to me. So you need to understand how to solve problems, and you all have that down. By the end of this class, you know how to solve problems. You need to have a good idea or a good problem you want to solve. And then the last thing you need in computer science is a programming language to solve it in. So the point of 106B is to learn the hard, challenging concept, which is how to solve problems. But what happens is a lot of students leave this class having a really thorough understanding of programming, but maybe like they don't have a standard language to program in, and then they go into interviews, they write vector with a capital V, and then their interviewer's like, "What's that?" Right? And it shouldn't matter, but some interviews do make a big deal of it. So the kind of focus of 106L in this class is going to be the programming language of those 3 steps, basically. Okay, so so before we begin, maybe it's a good idea to talk about why we should learn about C++. So I'll go through this kind of quickly. But C++ is this really great language that lets you like program in whatever way you want. If you want to do object-oriented, you can do that. If you want to use it like C, you can do that. There's very functional paradigms in C++ too. But in general, like it's just a really popular language. Here's like a list of most popular languages by this index that's compiled. C++ is always in the top 5. It's one of the most loved languages on Stack Overflow. It's used in an incredibly vast array of companies. You can see a bunch of big names there. It's used basically for every browser that's written. It's used in software. It's used to implement Java's runtime, actually. So that's a fun fact. And it's used in games and other really cool systems-related things. So it is really like a incredible language to try and learn. So I'm going to kind of motivate what kind of cool features we have today. Okay. If at any time you have questions, please feel free to stop me. I'm going to go. We have way more material today in my slides than I think we can cover, because it's 10 weeks of a class kind of condensed into one. So we can go at whatever pace you feel like going at. Okay. Cool. So we're going to start off by talking about this really cool C++ feature called templates. And we're going to start by motivating this idea with a problem. So we're going to see a problem that people experienced when using C++, which led to the introduction of this feature. Okay, so here's like this scenario. Here's the game we're going to play. So let's say you're doing you're programming along, and you decide for some reason you need a minimum function that takes 2 integers and returns the smaller of the 2 integers. It's like a reasonable thing to do that comes up from time to time. Right? So how you would write this function? Well, you would have a function that takes an int a and an int b, and then if this notation is not familiar, it's fine. It just says if a is less than b, return a, otherwise return b. Okay? So just doing that concisely because I didn't have space on my slides. Okay, so really reasonable. We use this function. We could pass it min of 3 and 5. It would tell us 3 is the minimum. Of 13 and 8, it would give 8. So what happens if we pass it the min of 1.9 and 3.7? What is going to happen when we do that? So this is a function that takes 2 integers, and we're passing it 2 doubles. What does it do to those integers? Anyone? There. Oh, yeah. Yeah, it truncates them, right? It rounds them down to integers, so it gets 1 and 3, and then returns a smaller one, which is 1. Right? So this is kind of an issue, and you decide, okay, well, I also want to find the minimum of doubles, so what do I do? Well, maybe I'll go and write another function that takes 2 doubles instead. So in sort of a C world, what you would do is you'd have 2 functions with the same name but different argument types. And then depending on what arguments you pass it, it'll decide which one to call. Right? So if I call min with 2 doubles, it'll call the second one. If I pass min with 2 ints, it'll call the first one. Okay? And you could sort of keep doing this for other types. You could have a min of ints, a min of doubles, a min of size t's, a min of floats, min of characters, min of strings. At some point you have to really stop and say like, okay, this is not a reasonable programming model for what I'm trying to do. Okay? So the issue with sort of doing something like this is that you have basically these multiple copies of exactly the same function, where the only difference is the type of the variables. And every time you want to add a new type, you need to go ahead and copy paste that function, change the type to whatever type you want. And if you edit the function even slightly, let's say you want like less than or equal to, rather than less than, you have to go to each of these and sort of replace the less than with the less than or equal to, right? So it's not a very like stable way of programming, especially if you have more complicated methods. And so the idea in C++, well, the designers were like, what is really different in code like this? So if we sort of look at this, what is the like fundamental difference between all these implementations? Sorry? Yeah, so, yeah. Okay. Okay. Okay, so yeah, like the main difference, if you look at it, is just the type, right? It seems like the type is the only thing that changes between this function. So if only like there were a better way to do this sort of blueprinting of a function with some sort of generic type. And that's kind of what the idea of templates in C++ are. Templates are really just a blueprint of a function that lets you use this exact function for like different types. So thinking about how we wrote all our min functions, we only changed the type. So if you look, we had our min function. All we did was replace the int with a double, and then we had the other version of it. So the idea with templates in C++ is we're going to give the compiler this template function and tell it what specific parts, what specific types should be general and should be replaced when we use it in a specific way. So the way this looks is, let's say we have our minimum function, again, on ints. And what we're going to do is make this a general template function. So rather than having ints, we're going to say, make it some generic type t. You could call it whatever you want. I'm just going to call it capital T. Okay? And then all you have to do is tell the compiler T is a generic type. And so just by doing these two things, you now have a min function that will work on any type, basically. Okay? And that's really powerful if you think about it. So just as an example of how you would use this, let's say we've written this min function as it is. You can indicate the type of the function you want to call by specifying it in angle brackets. So let's say I have two integers and I want to find the minimum of these two integers using my template function. I would say min with the type int, replacing the template parameter, and call that function on A and B. Right? And if I had double, I could do the same thing. I could call min with the template parameter being type double and then call A and B. Okay? And so how this literally works, which is like sort of an interesting question too, is that let's say you're the compiler and you're looking at this code. And you're on this line, you say, okay, the user declared two ints, an int a equals 3 and a b equals 9. That's fine. I can do that. And then the compiler gets to this line and it says, I don't have a min int function. No one ever defined a min int function anywhere. But I do know how to make one. Someone told me, gave me a cookie cutter template of how this function should look for any type. So I just have to go and like replace that type with this type, and that will give me the function I want. So what it does is like literally, in a very literal sense, it takes this template function and then generates this function from it with the type t replaced with int. Okay. And so when you use this, actually, most of the time you can leave out the angle brackets too, because it infers from the type of the parameters what version you're calling most of the time. So you really have like something that looks like a min function but works for any type. Any questions about this so far? Yep. Sorry? Yeah, so the question is, what happens if we call like min on, say, 3 and 2.9? So you have different type parameters. Which one will it use? That's a very good question. So either like sort of two reasonable guesses. One is it's going to convert one to another type, or the other is it's not going to compile. And actually it errs on the side of not compiling so that it doesn't do anything unexpected. It'll say ambiguous call could not infer template type or something like that. It's a very good question. Yep. Yeah, so that's a very good question as well. The question is, if we go back to this function here, what if we pass in two types that don't have a comparison operator? Will this compile or will it not? And so the answer to that is in like 2 slides, but in short, it's not going to compile. So the thing with template functions, and this is a great point, is that there's this sort of implicit idea that any type you instantiate your template for should be able to do everything you use it for in the method. So in this method, we were comparing 2 types, right? And so if you pass it a type that can't be compared, it won't compile. In the same way, if we were incrementing one of the types in that generic method, if you pass it a type that doesn't have an increment operator, then it won't compile as well. So that's something called the implicit interface of the template, which is that the only types valid to use with a templatized function are those that satisfy its implicit interface, which is basically if you replace this type T with the actual type you want to use, would the code compile? And if it does, it will compile. If it doesn't, it won't. Okay? And this is actually an important point. It will relate to something we'll talk about in a bit. Okay. Any other questions about templates? Okay.
Is there a way to limit the scope of the template? Not all types, but
Yeah, that's also a really good question. There is actually, and it sort of amounts to this hacky thing where you do something to the type in the method that would only work on certain types, and so it won't compile for the other types. It roughly amounts to that, but in a like more elegant way. But yeah, you can definitely. Okay, cool. Any other questions? Okay, so let's check the time. Okay, so one sort of question for you all is, nope. So where have you seen this kind of notation before, where you have like these angle brackets and then you're telling it a type or something? Anywhere? Is that a hat? Yeah? Yeah, so when you make a vector or map, you also do something like this, right? You say vector angle bracket int or vector angle bracket string. If you've ever wondered how that works, the idea is exactly the same as template functions, except it's called templatized classes. And what that looks like is basically just like how we generalize functions to any type, you can also generalize classes to any type in almost the exact same way. There are a few more quirks to the implementation, but it's the same idea morally. So for example, what we're going to look at today is you wrote this array stack class a few weeks ago when you first learned about memory management, and we're going to talk about how you could make that array stack work not just for integers, but for any type. So you had this array stack class which had a push method and then some other methods, right? And so I'm going to show you how you would templatize this class so that rather than only operating on ints, it's going to operate on any type. And the idea is similar. So firstly, we have our .h file and then our .cpp file. And I'm only looking at one of the functions right now. But okay, so the first thing you do is what we did with functions, where you replace the int with a generic type, let's say t or value type. I call it value type because I think it's a clearer name. Okay, and then you just tell the compiler that value type is a generic type by adding this line at the start of the class. Say it's templatized over this type called value type. Okay, and then you have to sort of do the same thing in the CPP file. You have to firstly change the array stack object to be array stack value type. And then above this function implementation, you also have to say value type is a templatized type. So it's kind of annoying where like for each function, you have to prefix it with template type name value type, and then change array stack to array stack value type. Okay, so I guess there's a typo because this should also be value type, but ignore that. Okay, and then the last thing you have to do, which is kind of annoying and doesn't make sense, is to move all the CPP file to the end of the .h file and delete the CPP file. So for some reason, the way templates and compilation in C++ work, you can't have template code split between interface and implementation. They have to be in the same .h file at once. So if you've ever looked at Stanford's collections, all the vector, map, and int stuff are in the .h files, and there's no CPP file for them. Okay, cool. So yeah, so I thought it would be fun if we just sort of look at this array stack code and then just templatize it a little, or completely, I guess. So just as a refresher, we had an array stack, which was a stack backed by a heap allocated array. So we had an array of ints called elements. It has a size and capacity. And we had this like push, pop, peek is empty, and two string methods. So how this is being used is we have a main function that, I guess this shouldn't be there. So we have a main function that creates an array stack, pushes some integers into it, and this prints some things. Okay. So what we're going to do is we're going to make this work so that we could push. So right now, if I do stack.push, let's say a string, it's not going to compile because it says you're trying to insert a string where it's expecting an int. Right? So this is not a generic stack. It only works for ints. So what we're going to do is we're going to go to the .h file and then templatize this. So what we're going to say is this is a templatized class, and it is templatized over this type called value type. Okay, and then so let's do this sort of interactively. What should I change to a value type here? Should this be a value type? Anything in this method? Yep. Yeah, so the int needs to be a value type because now it's operating on a generic type. Okay, what about pop? Okay, so int, it should return a value type. Peek should return a value type. This should still be bool because it's just checking if it's empty. This will still be a string. Over here, we don't want an array of ints anymore. We want an array of value types. And then size and capacity. Ah, shit. Sad times. Actually, is there an outlet here? Okay. Okay. Anyways, thank you. All right. Okay, so so we've templatized based on value type, and I think those are all the changes you need to make here, except we now have to go to the CPP file and make these changes too. So if we go to the CPP file, we have all these things. So remember, we need to templatize each one and then say it is not an array stack, but an array stack of value types. So rather than in the array stack class, it's in the array stack value type class. And then we want to copy this template thing above each of them too. So I'll do this really quickly. Okay. And then template. Okay. Cool. And that's almost it. We just have to do one more thing, which is, sorry, these should be value types. Value type, value type, value type. Okay. And what we have to do is move all this code to the CPP file, so to the H file. So we'll just go to the bottom after the class is declared and just throw that in there. Okay, and then we'll just delete all of this and maybe delete the file. Okay, and now the code is compiling, but sorry? Yeah. So, oh, does it? Oh, yes. Oh, perfect. Right. Value type result. Right, perfect. Yep. Perfect. Okay, great. Thank you. Okay, and it does compile at this point, but it's giving an error saying use of template array stack requires template arguments. So because now we've generalized it in main, we can't just say array stack stack. We need to say array stack int stack, and then it'll compile and it'll work supposedly in the same way it was before. Okay. Cool. So any questions about that? Okay, great. So that's basically templatized classes in a nutshell. There's some details where you have to move everything to a .h file and then prefix everything with template type name and some weird syntax, but this is roughly the idea. So if you go to Stanford Library Collections, let's say vector.h, what's the first thing you see? It's templatized over value type. And it has a constructor and all these things. And the implementation is in the H file. So it's really like things you can understand. Okay? Cool. So that's sort of one topic. Now we're going to move to the next topic. Okay, so you've been using these things called vectors, stacks, maps, and queues your whole life, or these 10 weeks, I guess. Yeah. So I just wanted to point out that these are like very real-world concepts. In C++, in standard C++, those exact collections exist, more or less. So there's the standard C++ library, which has a set of classes and algorithms. So it has these container classes called lowercase vector, lowercase map, lowercase set. And these algorithms sort, find, which we'll talk about in a second. And the Stanford C++ collection acts almost like the standard ones, except the standard C++ collections are really, really unfriendly if you're just starting off programming. So just simple examples, if you go out of range on a vector, it's not going to crash. It will just go out of range, and maybe it'll crash because you corrupt your memory, or it'll just work and you'll never know. So the Stanford C++ collections do effectively what the underlying standard C++ collections do, except they have better error messages and they're simpler to use. And it's because like if you're C++ programming, there's sort of a paradigm you need to adopt, and we don't want to waste time in B teaching you that paradigm when you should be focusing on learning the concepts. So just sort of a summary. So we have Stanford on the left, standard on the right. There's no graph class in the STL, in the standard library. There's no grid. There is a hash map. It's called unordered map, hash set, unordered set. Vector is lowercase vector, linked list is lowercase list, map, set, set. Okay. We also have priority queue, which is lowercase priority queue and all that. So there's like this trend where lowercase single letter is usually what exists in the standard library. Okay. And just sort of, there's some method differences too, but they aren't huge. But I have a reference here if anyone wants to look at it in their own time. So we have Stanford vector on the left, standard vector on the right. Everything looks the same except this. Instead of calling .add to put something to the end, we call .pushback because you're pushing to the back of the vector. You call to get an element, the standard vector bounce checks by default. Standard vector doesn't. If you call v.at, it will bounce check. And then it's the same thing with inserting. And then you have sort of basically everything else the same. So like biggest takeaway in an interview, don't call .add, call .pushback. You look like C++ and it'll be great. Okay. So just as an example, we have just code using the Stanford vector, and we're going to like convert it. The first thing we need to do is lowercase the v, include so we have to include the standard vector, which is with angle brackets because it's a library vector. We lowercase the v, we change the .add to .pushback. And notice we had v.insert at index 0, the value 42, and now we have v.insert something called v.begin, and then the value 42, which we'll talk about in a second. And in Stanford vector, you have v.remove with the value 2 at index 2, and then in the standard vector, you have v.erase, and then again this begin thing, and then +2 for some reason, which we'll talk about in a second. Okay, so any questions about the standard collections at all? I know I'm really rushing through these things, but I want to get like a breadth of things. So, okay, great. So, what's next? Okay, so let's talk about these things called iterators. All my L students are laughing because this is like 10 weeks. Literally, we're at week 4 or 5 right now. So, okay, so let's talk about iterators and what these are. So again, it's worth talking about these by motivating a problem that led to their invention. Okay, so what iterators are motivated by is this idea is like, how do you iterate or how do you loop through an associative container? An associative container is a map or a set or some like unordered collection, which is like not a vector. It doesn't have an inherent idea of ordering. How do you loop through those containers? So with a vector, when you loop through it, you have indices int I equals 0, I less than v dot size I plus plus. But with like a map or a set or something, what sort of notion exists to do that? Well, you can't set I equal to anything like the 0th element because it's not really ordered in any way. You can't check what I is less than because there's not really an end element because it's not a sequential container. So like what do we do with this problem? And so C++ had this really neat solution, which was like, let's take indices and sort of abstract them into a more general setting that will work on all containers, regardless of what the underlying container is. So the idea is we're going to try and behave like indices do, but work more generally in cases where like indices wouldn't normally work. So the idea is an iterator, or iterators are these generalizations of indices that store position within whatever collection you're at, and you can move them forward, you can compare whether you're at the end, you can get the start one, and they allow you to traverse over any collection, is the idea. So sort of the mental model of iterators is like, you have some collection, and like think of it as a cloud, because not every collection is a sequence. So a more general way of thinking about a collection is some cloud of things. Okay, and the idea of iterators is they let you view this non-linear collection in sort of a linear manner somehow. So yeah, the question you might be asking is, how does this magical great thing work? My answer to you is we don't care right now, because we're going to trust that they work, because we're going to let the abstraction of iterators do their thing. We're just going to learn how to use them, and if you want to learn how to implement them, take 1 or 6 hours. Okay. So, so we'll just use them for now. But the idea is pretty intuitive if you keep in mind we're trying to behave like indices but work more generally. So let's say you have a collection and the iterators are letting you view this collection in a linear manner. So if you had indices, you'd say, let me start at the 0th index. Well, if you have iterators, you say, let me start at the begin iterator. So you call your collection's variable name .begin, and it'll give you an iterator pointing to the start of the sequence. And you want to store this in some sort of variable. So you'll store it in some variable called iter, and it has some type. And that type is actually defined in the class that you're using. So if my set is a set of ints, then in the set int class, there's an iterator type that you will refer to when you want an iterator. So just to recap, you're getting the 0th index iterator, the beginning iterator, and storing it in a variable. And the type of this iterator is this thing defined in the class. Okay, so what this looks like is that you have an iterator pointing to your 0th index, your begin, right? Now, if you want to get what's actually at the end of this iterator, so this iterator is referring to something, if you want to get what this iterator is referring to, you dereference it with the star operator. So if I want to print the current value of iter, I would do cout star iter endo. Okay, and that'll print the 1. Okay. Now, what do I want to do? I want to move to the next thing in my collection, right? So I advance my iterator by calling ++ on it. So I say ++ iter, it will move to the next one. And then I can again print it by dereferencing it, and it'll print the 2. I can advance it, print it, advance it, print it. And then somehow I need to be able to check if I've reached the end, right? So if we're modeling indices, we have 0, and then we have I less than v dot size. Or we want to make sure, we want to stop when we've reached 1 past the end of our collection. So with iterators, you can do the exact same thing. There's something called the end iterator that you can compare yourself to. And the end iterator is 1 past the end of your collection. So you can terminate by saying, if my iter is at the end iterator, then stop. Okay? So it really is not behaving any differently to indices, but it'll work in a more general setting. And that's the powerful idea here. So sort of the summary is you can create iterators, dereference them, advance them, and compare them. Now, if any of you are wondering, this looks a lot like a pointer. the idea with iterators was, let's try and make them look like pointers. Now, it's worth asking why anyone on Earth would want something to look like a pointer if it doesn't need to be. But the idea was, like, programmers were very familiar with the idea of pointers. So they made iterators, the syntax of iterators, to look and behave like pointers would. Because all pointers are iterators, but not all iterators are pointers. Yeah, is the idea. Okay, cool. So sort of looking at code, if you had a vector in V, you added stuff to it, how you would loop through it in a for loop. So normally, if you had a vector, you'd have for int I equals 0, I less than v dot size plus plus I. Now you have vector int iterator. The type is the iterator in the vector int class. Started off at v dot became, our 0th iterator. Keep going until we hit the end iterator and increment it each time. Okay? Any questions about this? Okay, so cool. So sort of some more things about iterators. Most standard, actually every standard collection has iterators that you can use. Even vector, which you can index into, it is suggested you use iterators for. So when you operate on vector and you call insert or erase, you don't tell it what index to insert to or what index to erase from. You tell it what iterator to erase. So that's why we had v.begin plus 2 when we were removing at the second element rather than v.erase 2. Okay. And so just a sort of quick question for you to ponder. Given what we know about templates and this implicit interface where a template will compile if whatever type you pass it can call those methods in the template function, do you gain a lot by having this standard interface of iterators? And sort of what might be something there. So I'm not going to, it's just something for you to ponder. What do we gain from having a standard interface of iterators? Okay, so this leads directly into this next idea, where in C++ you also have these things called algorithms, which are basically like a programmer's dream. It's like some really intelligent people sat down and implemented all these algorithms, and they'll work on any class that has iterators, right? So the sort of the motivation of algorithms was, let's say I want a sort function. Okay, I could write a sort function that will take a vector of int and sort it. Or I could write a sort function that will take an iterator start and an iterator end, sort everything in that range. Now this sort method will work for vectors, lists. It'll work for, I guess, any collection that provides iterators, more or less. Okay, so with standard algorithms, they operate on iterators, and they that lets them work on a lot of types. Sorry, and they rely heavily on templates. So here's a list of all algorithms. So there's some really useful ones. So standard copy, which copies from one iterator range into another. You have standard equal, which checks if the range is equal to something. You have max element, which returns the max element in an iterator range. You have, I don't know, let's see, yeah, other things. I have like this fun story of algorithms where I was in a programming interview and the person was like, yeah, so he was asking about something about some sort of modified binary search where you don't want to find an element, you want to find the greatest element less than or equal to something. Right, so like the greatest, the least upper bound of a given element. And it's like a modified binary search that you can do. And I did it in one line because there's an algorithm called standard upper bound that does exactly that. And the programmer and the interviewer was like, I have no idea how that works. And I was like, it's n log n. It does it's log n. It does a binary search. And he was like, yeah, okay, cool. Let's move on, right? So really, when you like master algorithms, programming in C++ is like incredible. So if you like ever look at like the international programming competition or something, almost always the top team uses C++ because what do they have to do? Well, they write a collection, provide iterators for it, and then they can use these algorithms on it perfectly without having to do anything on top. It really is a powerful concept. Okay, so we might not have time to actually go through some of these algorithms, but I definitely encourage you to look through them. Any questions so far? It doesn't need to be something specific. If you have just like a general question around these topics, I'll take that too. Okay, cool. So, so that's sort of week 6 of 106L. And now I think just to sort of close off, we can talk about some other neat features that are really cool. So the first thing I want to talk about, and again, disclaimer, don't use this in your final exam. People have done it before and it hasn't worked out great. So just compartmentalize this outside of 106B. So a really neat feature in C++ is this thing called auto, which is it's this really cool C++ feature that lets you type deduce the type of a variable. So the idea is if the type of a variable is obvious, right? So I have int x equals 3. You're saying x equals 3. It's obvious that 3 is an int. So I could probably tell the compiler to figure out that the type of x is int. So what I can do is write something like auto x equals 3, and the compiler will figure out that the type of x is an int. And so I'll show some examples of using it. But you shouldn't abuse this, but you should use it as much as possible in real life, not in your final. The idea is like whenever the type of something is really obvious, you should use auto. And there are also some places in C++ that's kind of advanced, but you don't know the type at compile time. And so you use auto there too. Okay, so just sort of an example, you could have auto x equals 3, and the compiler will say, okay, x is like an int. I can figure that out at compile time. You can say auto vset equals graph.get vertex set, and they'll figure out that vset is a set of vertex stars by looking at the signature of the get vertex set function. And sort of the most useful place of auto, I think, is like in iterators, you saw that the type of the iterator was this like ghastly thing where you had like set, int, colon, iterator, and that was the type, right? So it's also very nice to be able to do auto it equals vector begin. So this is the most common use case of iterators, of auto, I think. Okay, so one sort of side note related to this, in CS106B, how have you been looping through a set, for example? This is just a question you should be able to answer, hopefully. Yeah. Yeah, so you had something, I think, let's say you had a set int b 314, okay. Let me just include set.h. Okay, so far, when you've had a set, how you loop through it is what you said was for int x in, let's call this s. For int, or let's call it my set. So for int x in my set, let's say cout x, right? And that does this thing where it prints. Sorry. Okay. So that does. Oh, God damn it. Okay, so it does this thing where it prints. Nope. Okay. Okay, it's printing down here for whatever reason, but ignore that. Okay, so it prints everything in a set. So actually, this thing is shorthand for sort of the iterator code. So actually, before we do anything, how would you write this with iterators? Well, you'd say for auto it equals my set.begin. So for I equals 0, but on a set now. It not equal to my set.end. Advance it, and cout, or let's say int x equals the thing it is pointing to, and let me cout x. Right? So if I run both this code, it prints the same thing twice. And actually, this for each loop does it is syntactic sugar for this like cool thing over here. It's just a shorthand for it. So actually, the Stanford set and Stanford map provide iterators, which is what lets you do something like this. So if you provide iterators to your collection, you can use this notation, and it'll compile and loop through. So the for each loop is shorthand for this whole thing that we talked about. Okay, so another thing that we probably won't talk too much about is we have this thing called lambdas, which are inline functions in C++. It's really neat once you get used to them. These exist in a lot of languages, but the idea is basically that you can make functions on the fly. Instead of declaring them as a function, you can make them a variable. So it sort of looks like this. Forget what the capture list is for this class, but you have the parameters of the function, an arrow, and then the return type, and then you just write the function like you normally would. So as an example, you have a print int function that, forget the capture list, it takes an integer parameter. It has return type void, so you can leave the return type out. It's coutts exendo, and then terminates that function. And so you've stored that function in a variable, and then you can call it like a normal function. You can do this inside like another function, so it's like really cool. Another example is if you want to use the sort algorithm. So the standard sort algorithm takes an iterator range. So you're saying sort the range v.begin to v.end, and then use this comparison function. You can pass it a comparison function that, given two ints, says that sort them based on the fact that I is greater than j. The first one is sort them in reverse order, basically. Okay, so these actually exist in almost every modern language. So they exist in Python, definitely, JavaScript, Java even, God forbid, and then C++. So really cool advanced C++ topic. Okay, so we have about 2 minutes. So I just wanted to wrap up by looking at this really cool thing, which is I was looking for a good example of real C++ code that's like well written. And as much as I hate to say this, the Bitcoin source code is incredibly well written. So we're gonna, I'm not about the hype, but like the code is really well written. So I thought we'd just look at it really quickly and sort of see some of the things we've talked about today. So this is the Bitcoin source code. It's on GitHub, right? And then you go to the src folder and you notice lots of C++, so .h and .cpp files. Right, so anyone want to pick one to look at in particular? Chain.h, coin, what? Okay, let's do coins. So we have coins.h and coins.cpp, so it sounds like it's probably a class. So let's look at coins.h. It's a class that has some other classes in it. It's initializing some things, and it has some methods. It has some templatized functions that will operate on any stream, it looks like, whatever that is. And some other classes in here. And if we look, we have an unordered map, which is a hash map, and things like that. If we look at the CPP file, we have the same thing. You're implementing the coins class. Look, it returns an iterator for the coins class, right? Right, if iterator is not equal to cashcoins.end. So really, like, I'm not bluffing. Like, this is actually how C++ code is written. You don't use indices. You use iterators. Use .inplace and all these ideas. Again, another iterator, and so on. So I'd encourage you to go kind of like look through that on your own. But I think that's it. So thank you.